In this video, I'll explain the working principle of CMOS inverter with the fluid analogy. Stay tuned till the end of the video and your concept of CMOS inverter will be clarified. Yeah, here we go. So in this video, let us try to understand the working of CMOS inverter with fluid analogy. So I have drawn the CMOS inverter schematic here and the transfer characteristics, that is input versus output voltage. So let us see the schematic. CMOS inverter is having a PMOS transistor and NMOS transistor. The source of the PMOS is connected to VDD and the source of the NMOS is connected to ground, VSS. VDD is positive voltage 5 volt. Example. And both the drains of PMOS and NMOS are connected together and the common point is taken as output. And both gates of the transistors are connected together and the input is given to that. And the output I have connected to a load capacitor CL here. Now here I assume that the PMOS transistor is having a threshold voltage of -1 volt and NMOS is having a threshold voltage of +1 volt. And I assume also that PMOS and NMOS transistors are balanced. This inverter is balanced in the sense that they give the same drive current for the given VGS and VDS. The W/L ratios of the transistors are adjusted in such a way that they give the same driving currents for the same VGS and VDS values. Okay, so for this case, let us try to understand first the transfer characteristics and its regions of operation, and then we'll try to understand that with fluid analogy. So when input is changing from 0 to VDD, so here VDD is 5 volt, 0 to 5 volts, and output also will vary from 0 to 5 volt. And how it varies, let us try to understand. So initially, suppose when Vin equal to 0, the NMOS transistor is getting a VGS, gate to source voltage of 0 volts. So it will be turned off, it won't be turning on until VGS is greater than the threshold voltage, that is +1 volt. Until that, this will be off. Of course, there will be some leakage subthreshold current. I am assuming that subthreshold current is 0 here. So it is in cutoff region when Vn equal to 0, and that is giving maximum VGS to the PMOS transistor. For the PMOS, gate to source voltage has to be negative, but here we have a positive VDD and Vn is 0. So that is equivalent to giving a negative voltage to the gate when if you consider this with respect to source, equivalent to -5 volt here, or minus VDD when Vn equal to 0. So that is making the channel here for the PMOS transistor, and for current to flow from source to drain, there has to be a negative voltage from drain to source. And that is also, there are no negative voltages here, but only the relative voltage we have to see here. The relative voltage from drain to source here is again negative because V0 is always less than VDD. This is a intermediate node voltage that is supposed to be, that is expected to be less than VDD all the time. So that is making VDS for PMOS also negative and VGS for PMOS is also negative there. So that is turning on the PMOS transistor. VGS for Vn equal to 0 for PMOS is minus VDD and VDS is V0 minus VDD for PMOS transistor. Alright, so here V0 minus VDD is some value. We don't know how much V0 will be there. This is getting charged to the full extent. The V0 will keep on changing and there is no discharging current here because NMOS is off. It is charging to the full extent and the node voltage will reach to that of VDD here when Vn equal to 0. So we are assuming that there is no leakage current, subthreshold leakage current. Alright. So as you increase further, the Vn voltage is suppose making it to 1 volt, which is equivalent to the threshold voltage of NMOS. When Vn equal to 1 volt, what is happening? It is just at the onset of out of the cutoff region, but still there won't be any current flow, and only PMOS is conducting. VGS for PMOS is -4 volt and it is connecting. It's in the linear region, and that will keep on increasing the voltage here, and it will reach to again up to VDD there. Okay, maximum voltage. And when it is more than 1 volt, that is the VTN, threshold voltage of NMOS transistor, what will happen? The NMOS will be turning on now. So that I am talking about the region 2. First one is region 1 where NMOS is cut off and PMOS is linear. And in region 2, NMOS is getting some VGS more than VTN, then that is making this transistor to operate in saturation region. Alright, it makes it operate in saturation region because it is already full. So VDS is large and VGS is just above threshold, and this is making the NMOS transistor in saturation. If you look at my other videos, there are 3 regions of operation for a MOS transistor: cutoff region, linear region, and saturation region. Okay, so NMOS is now in saturation region in region 2 here, and PMOS will be in linear region. Okay, so in the saturation region, the MOSFET acts as a current source, constant current source, a voltage controlled current source. So the current through this does not depend upon drain to source voltage. Even if you increase the drain to source voltage, the current will not change. So it is fixed by VGS, gate to source voltage. Whereas in the linear region, for a given VGS, the drain to source current will keep on increasing linearly. That means it is in the resistive mode. That is a linear region. Okay, so here in region 2, I have applied a gate to input voltage that is acting as VGS for NMOS transistor, just turn on, and NMOS is now acting as a current source. It is just sinking some constant current from this node. And because of the Kirchhoff's law, the current which is entering into this should be equal to the current which is leaving the node. So the current which is entering the node will now has to adjust itself, and that should be equal to the current leaving the node. So the node voltage will now adjust itself until the current which is entering into this node, that is through the PMOS transistor, becomes equal to that of the current that is leaving the node, which is equivalent to the current through NMOS transistor. So the current which is passing through the PMOS transistor is now in the because PMOS is in linear region, so that is now depending upon the VDS, drain to source voltage, that is V0 minus VDD. So V0 will keep on reducing. That makes V0 minus VDD will be reducing. Will be increasing further. Okay, sorry, it will be increasing. So when V0 minus VDD is increasing, the current will be keep on changing. Alright, so it will keep on changing, and the current will becomes until the current becomes equal to that of the current that is sinking here. So then it will settle at a particular V0 will settle at a particular voltage. So for example, when V in equal to 3 volt, it will settle at a particular level here when the current through PMOS and NMOS becomes equal. The charging current and discharging current will becomes equal. So there won't be any further change of the voltage here. So it will settle. We are giving enough time for this voltage to settle. So we are not doing a timing analysis here. This is just a DC analysis. We are talking about DC transfer characteristics. No time is coming into picture. So we are giving enough time for any particular given input voltage, and we are finding out the output voltage, giving it enough time to settle it down. So in one point, when V in equal to VDD upon 2, that is halfway through the maximum voltage, what will happen? VGS for NMOS and VGS for PMOS are now exactly equal. VGS for NMOS is 2.5 and VGS for PMOS is minus 2.5. So I have just designed the inverter balanced. That means both are giving the same currents when they are applied with similar voltages across their terminals. So now what will happen? This node voltage will now try to settle in the middle point again. It will come back to middle point, VDD upon 2. Suddenly, all of a sudden, for a moment of time, just at the middle. So as you increase it further a little bit more than 2.5, that is VDD upon 2, what is happening? That is entering into another region, that is region 3 there. In the region 3, now the PMOS transistor is now going into the linear region, and PMOS transistor is going into the saturation region and NMOS going into the linear region. When V in is more than VDD upon 2, that is in the region 3. For example, you make it say 3 volts, input as 3 volts. So that is making VGS for NMOS as 3 and VGS for PMOS is minus 2 volts only. So that is making it a saturation region, so as the PMOS transistor will act now as a constant current source. It will pump constant current, and irrespective of the node voltage here. The current does not change with the node voltage at the output here. So a constant current is being passing through this. Now the voltage will now has to adjust to a particular level until the current now passing through the NMOS transistor, which is in the linear region, now has to become equal to that of the current which is coming through the PMOS transistor, which is acting as a current source. Alright, so the output voltage will settle at that particular level. So that is what we are giving enough time for this to settle. So now the output voltage will settle at a particular level, somewhere around here, say maybe 0.5 volts. So that makes VDS of this NMOS transistor, which is there in the linear region, so that at that particular voltage the current through NMOS will now become equal to the current which is passing through the PMOS, which is acting as a current source over there. Now if you increase it further, more than 4 volts, exactly at 4 volts means what is happening? VGS is 4 for NMOS and VGS for PMOS is just minus 1 threshold voltage. If you increase it further, say 4.1 volt, so VGS for PMOS is 0.9, minus 0.9, that is less than the threshold voltage there, but here it is having more voltage for NMOS. So the PMOS will be cut off for Vin is greater than 4 volts. That is region 4. PMOS is cut off and NMOS is in the linear region. There is no current coming here, so eventually there is no charging current. The entire charge will be discharged through this NMOS transistor and it comes to 0 level. So that is the shape of this transfer characteristics. And what is the slope of this? It may change the shape. It may be like this or like this. So that depends upon the geometries here that we can see in the other videos, and how it becomes and how it varies its shape, and the transition point also may be shifting towards left or right. These all things depends upon the geometrical parameters of these transistors that we see in next video. And now in this video we'll try to understand the same the transfer characteristics with a fluid analogy that makes very clear to us. I have just drawn a diagram here. There is a big tank of water. This is very big and which is filled to a particular level, and even if you draw some water from this tank, the level does not change. Now this big tank of water is now representing the power supply, and the level is representing the power supply voltage VDD. Alright, so I have connected this tank to a bucket, a small bucket, which is representing the load capacitor here, a small bucket, and through a pipe, filling pipe, and that pipe is representing PMOS transistor there. And now that is also having a tap like this, a tap, and also there is an outlet from this bucket, a tube, and this tube or pipe is representing the NMOS transistor there. So I have also a pipe to that, a tap to that, like this initially, so for example, and the level of this, level to which it is filled, that level will represent the output voltage, and the force that I am applying on these two taps simultaneously, that is representing input voltage. Okay, so the arrangement of these taps is such that when you are opening one tap, other tap is being closed by the same amount. So that is the arrangement we have here. Alright, so when one is opening, other is closing by the same amount. Now just look at it. When the input force is 0 initially, the right side tap, the outlet tap is closed completely and the inlet tap is opened completely, slightly above this the top edge, slightly below the bottom edge here. So that is equivalent to the input voltage 0 there. So that means when input force is 0, equivalent to input voltage 0. So what is happening here? There is a flow of water from here. Just keep on filling filling it. There is no outlet, so it is not going out. So eventually the water level in my small bucket will be filling, slowly filling, and I am giving enough time, and it will come to the maximum height, the height which is same as that of my bigger tank which is supplying it. Okay, so it is filling to the maximum level. That is, say, analogy for this is up to VDD. Okay, so it is filling. So you can see in this transfer characteristics, when input is 0, that is the force is 0, output is going up to VDD. So this is output actually. The level of this is nothing but the output voltage. The level, the height of this. Okay, so now when I apply some force, a little force, which is equivalent to 1 volt there, so that means it is coming up to the edge, top edge, and this is going up to the bottom edge there. Okay, so even then there is no outflow here, only the inflow. The level does not change, it remains at the maximum level. There is no outflow. Okay, it's remaining there. So when I apply some more force on this, which is equivalent to 2 volts, what will happen? This is slightly closed and this is slightly opened. Okay, now here we can see, so what will be the level now? The water is flowing from tank to this, the opening is more, the outlet opening is less here. And here just listen, one arrangement, the tubes behave in such a way that when the tap is closed more than the half, below the half level, then the flow of the water does not depend upon the level difference, water level difference. Okay, this is ground level, 0 to this, it does not depend upon the height there. Whereas here also, when this is below the halfway through, when this is above the halfway through, that means it is only opened less than half of the tube, then the flow of the water depends upon the water level difference. Okay, so there is a water level difference here, there is no water level difference there. So now the outflow of the water here is less than, it is opened less than half. So that means it does not depend upon the level difference, that is 0 to maximum height. It does not depend upon the height. So even though height is changing, the rate of flow, the draining flow does not change. This is not changing actually. DR, draining rate, does not change. Only the filling rate will change. Now as we see that because it is opened more, it is having the tendency to fill with more water, but only less water is going out. So that the more water filling now has to be changed by the level here, such that the filling rate, which is a function of the opening as well as the height difference, when it is more than half, will now becomes equal to the draining rate. The draining rate is not changing with the height difference, as I said. Okay, yeah, so height will be settling somewhere there. So that is equivalent to, because here when you see, when input voltage is 2, that means the force applied on these 2 gates, which is equivalent to 2 volts, the openings are like this, so it is filled up to certain level, that is in between like 4 volts. The height is like this, 4, because now it is depending upon the height difference, h minus h1. Now when you make it further, like close just halfway through, and both are halfway open. Okay, so when it is just halfway through, both the filling current of the water and the draining current of the water will now does not change on the height. So the height will change suddenly. Initially it has just fall, and it will come back to a particular level just halfway through out there. When it is slowly changing, so it just comes at halfway through and it settles over there. So when the left gate is closed further a little and it is opened a little out there, which is now equivalent to applying a 3 volts on this. So what is happening here? the filling rate is supposed to be less and the draining rate is becoming more here. Now here, because it is less than halfway through, opening less than halfway through, now here the flow of filling rate of the water does not depend upon the height difference. So filling is constant, the rate of filling is constant. It is filling slowly because it is opened less, but the draining opening is more, so it is trying to take off more water. So both filling rate and draining rate has to be same. So to make them same, the height will adjust to a particular level, because here now it depends upon the level also, because it is opened more than halfway through. So it settles somewhere there. The height of this will be now around, say, 0.5 volt, which is equivalent to 0.5, somewhere like this. So when I apply some more force on this and just gone up to the edge, which is equivalent to applying 4 volt there, then what happens? There is no flow of water into the tank, only the outflow is there. Slowly it brings down to the ground level, zero level. There is no level, is zero there. Output, the height is nothing but your output voltage, that is becoming zero. So further making it down to zero there, when I apply 5 volt, what is happening? It is gone down little, even then it does not change. So like this we can understand the working of CMOS inverter with this fluid analogy. So we can also understand the working of a unbalanced CMOS inverter, and the different shapes of this transfer characteristics with the fluid analogy, and that we see in the next videos.